So today I'm going to talk, before I start, I want to emphasize something. I just happen to be the person speaking today. The contents of these slides were made by a lot of people, or the results of work from a lot of people from the computational X-ray science group and beyond. So we're a very eclectic group. We range from, crystallographers and theorists to people who have expertise in applied math and signal processing, high performance computing. And more recently, we're hiring a lot of young PhDs who come with a background in deep learning and automatic differentiation. I want to highlight three particular people whose work led to the results in these slides. The first is Anaka Babu. She was a postdoc with us till recently. She's now a staff scientist in a different group at the APS, and she's leading our AI at Edge program at the APS. Yudong Yao was a staff scientist with us. She was our expert in physics-aware deep learning. She's moved on to a very exciting role at the Shanghai XFEL. And Saugat Kandal, who actually got a PhD thesis with Chris Jacobson titled Automatic Differentiation for Coherent Imaging, but is now our self-driving experiments expert. Beyond the CXX group, a lot of people made this possible. In particular, Henry Chan, who's a staff scientist at the CNM at Argonne, and is an expert in molecular dynamics, among other things. And Ross Harder, who keeps us data science scientists honest to the physics of coherent imaging and from whom we learn more about coherent imaging every day. In addition to that, many of the people listed here played a very important role at the APS, the Math and Computer Science Division, the Data Science and Learning Division, Material Science, Center for Nanoscale Materials, folks at Lawrence Berkeley, and folks at NVIDIA, who we are collaborating more with as we move towards the hardware side of things. And funding from this came from Argonne LDRDs, AI CDI, AutoPhasennen, and an AI at scientific user facilities called Digital Twin for in silico experiments. So I'm going to talk about a couple of ways that we're using AI at the APS. And there's three main ways that we do this today. And we're starting to do this more in some and less in others. So the three main ways of doing this are AI to accelerate analysis. I'm going to show a lot of numbers in the slides about data rates, computational costs, and so on. And I'm going to show how AI lets us keep up with experimental data rates in a way that traditional methods cannot. The second main thrust area is in the steering of experiments. And kind of the idea is like, how do you, given a limited amount of time, which is a valuable commodity at a synchrotron or an XFEL, how do you maximize information gain for users? And then finally, something that's more nascent, but which I'm very excited about in the long term, is the idea that we could potentially learn physics directly from X-ray scattering data. So a lot of what the analysis that we do today, right, image reconstruction or spectral analysis and so on, are a means to an end. What we're really interested in is the physics of materials and the physics of something, and can we learn that directly from scattering data? And if I have some time at the end, I'll talk about how we are putting this into production and our plans for the next few years. So what I hope to kind of emphasize and convince you of is that AI is not a nice tool or a nice to have for us. It is a necessity for us to fully exploit instruments capabilities, especially in the APS upgrade era, which I'll talk about in a bit. I think it kind of helps to put things in perspective. The APS is, one of many synchrotron and XFEL facilities across the world. I believe there are more than 50 now across the world on every continent except Africa and Antarctica. And a lot of the problems and challenges that we face are also faced by other facilities as well. And these facilities enable these, a quite extraordinary scale bridging, multi-modal view of materials in operando. So to give you the idea of the scale at which we operate, going from left to right is big to small. So this is a picture of all of the APS. I'm told it fits a baseball stadium inside. And at any given point of time, we have 70-ish beamlines in concurrent operation. So each beamline looks like this, sits inside a lead-lined hutch. You saw several examples of this over the course of the week. And within the hutch, you have very different instruments at different beamlines, usually dedicated to some aspect of materials characterization. Pre-pandemic, we welcomed nearly 6,000 scientific researchers from academia, industry, and government from across the world. And all of them came to use these kind of unique, bespoke instruments, many of whom are multimodal, provide multimodal information about material samples. and which also makes data scientists' jobs kind of hard because each of these instruments are bespoke, and so you kind of need unique data flow, data and compute solutions to address it. Specific to coherent imaging, we are going to go through a big upgrade starting next year that is going to significantly increase the brightness and coherence of the APS. In addition to the accelerator and the storage ring being upgraded, we're also going to see new beamlines, so-called feature beamlines, like the one Ross talked about, the atomic beamline. We're going to have, I think, about 7 to 9 of them. In addition to those, you're going to see significant enhancements to existing beamlines that will take advantage of the increased coherence flux. So some of those are listed. So tachography is going to play a big role. We're going to have 5 to 10 beamlines doing tachography, something called coherent surface scattering, atomic that Ross talked about, polar, which is going to do polarization modulation spectroscopy, so vector tomography, CHEX beamlines are going to do Bragg CDI, XPCS, and so on. High energy X-ray microscopy, which is going to combine some diffraction microscopy with high energy BCDI, so to give you both very small field strain information at sub-grain level to many grains sample. And the 2600 probe, which is going to do 3D Bragg tachography, and many more. This is just a sample list. Bottom line is coherent imaging is very, very important to APS today, and more so in the APS upgrade. And this is, of course, going to come with a huge cost, which is in data rates 100 to 1,000 times. So why are we doing this, right? Just if we look at microscopy as an example, what these instruments enable, and Chris Jacobson gave a beautiful talk about this, is this idea that you could do scale bridging imaging. You could essentially, in a single instrument, access 5 to 6 orders of magnitude of length scales, while at the same time simultaneously imaging multiple different modalities, right? You can look at composition, structure, defects, oxidation state, strain, even photovoltaic response. You can do something called X-ray beam-induced current, and the idea is that you can focus X-rays down to a very small spot, like 10 nanometers or so, and so essentially measure the local photovoltaic response of a material and then correlate that to the local structure and composition and so on. The material scientist's dream, right? Being able to correlate local responsive materials to local structure to macroscopic device performance. And of course, because you're X-rays, you can do this under operando conditions of many different modalities, electrochemical, material, cryogenic, pressure, magnetic, and so on and so forth. So why AI, right? And the primary motivation that I'm going to talk about in the next couple of slides is the sheer data and volume, shared data volumes and compute requirements that are going to be associated with some of these instruments. So these plots that show here, I don't know how clear the text is on the screen, but this is a log plot of data in petabytes at the APS today and after the upgrade. So today we're about 10 petabytes or so. This is a similar plot from LCLS. They're ahead of us in data rates, as you would imagine. And this is a plot across the DOE light sources. And kind of the key point that we want to make is, from today to 10 years out, we're going to see 10 to 100x increase in data production across the different DOE light sources. This is an older plot, and if someone knows who the original author of this, please let me know. And what this shows is the photon flux over the last 60 years or so, plotted in comparison to Moore's law and storage density. And the key takeaway from this is that over the last 60 years, so photon flux, you could treat it as a proxy for information content, has been scaling faster than Moore's law. And Moore's law today is beginning to taper off, right? And so even if you argue, well, today we could just plug in a bigger supercomputer to keep up with the data and compute rates of the instruments, well, 5 or 10 years from now, we're going to fall even further behind. And so this is not a sustainable state of affairs. And so again, I repeat, use of techniques like AI are going to be a necessity to be able to fully exploit instrument capabilities, or we're just not going to be able to do it because we don't have the compute to do it, even at a place like Argonne, which is going to have the world's fastest supercomputer. And then again, of course, as you all know, the analysis of data from the APS involves solution of a lot of inverse problems, whether you're doing imaging or spectroscopy or diffraction. You have to solve inverse problems of some sort, and inverse problems are computationally expensive. And then the third big driver for us is our desire to do experiments with real-time feedback. And this kind of goes down to to another potential bottleneck in this era of high photon flux and high data rates. Today, a human sits in the loop, right? A human looks at the data that comes in and then decides, was that a good image? Was that something they were looking for? What does this contain some information that changes the trajectory of the instrument? Are you going to do something different? If you continue to do this, then the bottleneck becomes that human in the loop, making decisions on what data to acquire next in a sequential process. And so in this sort of conceptual example, if you're interested, for example, in material failure, material failure is a macroscopic phenomenon, but the origin of material failure is at the atomic scales, right? And so if you want to elucidate that behavior, you have to be able to interrogate very large volumes of materials, identify the position or the location of where failure is imminent, and be able to acquire data there at high temporal or spatial resolution. And you want to do this in an automatic fashion. So if you want to do this in automatic fashion, then you want to be able to have access to real-time processed data. And so you need to be able to invert data on the orders of seconds or less. And that is another motivation for using AI in the loop. So thankfully, we are co-located with some of the most powerful supercomputers in the world. This is Polaris, which is a top 20 supercomputer, which is online. And for the first time, which is very exciting to us, is that we have a direct integration between our supercomputers and our facility at the APS. So Polaris is a 44 petaflop machine, and a tenth of that machine, so about 4 petaflops, is dedicated for on-demand use for experimental facilities, particularly the APS. And so what that means is we have a direct pipeline from our microscope or instrument sitting at the APS directly to the LCF. And so we have workflows that can essentially take the data coming off the detector, move it to the high-performance computer, run analysis, send the solutions, and send the process data back to the beamline. And we do this both for traditional methods like phase retrieval or high-energy diffraction microscopy, as also for training deep learning models at scale, which I'll show in a couple of slides. Okay, so I'm going to talk, so we've had several wonderful talks already about ptychography, and I think I can skip some of this. Again, I want to emphasize the sort of sheer data rates that this involves. Chris Jacobson gave a really nice talk about how much volume you could measure at high resolution. I think my numbers are a bit more conservative, but I defer to Chris on this. But more importantly, kind of just to put things in perspective, this is equivalent to mapping out the entire USA at a few meter resolution in a few hours, except that you're not just taking a snapshot, you have to do phase retrieval as well. And so the data rate required to do that is equivalent to streaming hundreds of thousands or millions of HD movies simultaneously from a single instrument. Right? And we then have to do phase retrieval on top of this. So our approach is essentially, as Ross talked about a little bit, is to replace iterative phase retrieval with neural networks that directly learn to map the input coherent diffraction data to sample amplitude and phase. And so with ptychography, for example, you have to take overlapping data, which gives you the redundancy required to do the phase retrieval. With our approach, you do not explicitly use the overlap information. You directly measure the scan, the current imaging data at every scan point, and then you directly input that network and get a prediction of amplitude and phase, assuming that you can train the network, of course. So if you can do this, if you can train a network that is capable of doing this, as several speakers have already showed, neural network inference is hundreds of times faster than phase retrieval. And it also show you could also get by with significantly less sampling in real space. And I think George Barbatos showed examples of where you could even reduce the photon count to do this. And again, I want to emphasize that we are by far not the only people doing this. There are several groups across the world who are developing deep learning methods to replace the phase retrieval process. Teams at Brookhaven, Jean-Wei Miao's group, and many others across the world are doing this. What I'm going to address more specifically in my talk, right? So I think if we go through all these papers, it's fair to say that deep learning models can indeed replace iterative phase retrievals with a lot of constraints and riders and so on. And what I'm going to kind of address in the next few slides is how do we implement such methods on high rate instruments, and so be able to essentially do real-time imaging. So our approach that we took looks something like this. So there's a lot of things going on in this workflow. So let me break this down a little bit. So the idea is essentially this. We use our supercomputers to train our neural networks, do it at scale, but then deploy those on at the beamline running on edge computing devices. So this is what our workflow looks like. This is a schematic of the measurement, the tachography measurement happening at the beamline. As soon as the data comes in, we take those images, we send them off to our high-performance computing machine, in this case Polaris. We do phase retrieval. We do phase retrieval and then do supervised machine learning, again, in a distributed fashion on the cluster, to get a neural network that learns to invert the CDI data to sample images in phase. So the data moves to the high-performance computing, you do phase retrieval, do neural network training, push that to the edge computing device. This entire workflow is automated, and as soon as the scan is complete, this workflow gets triggered, the process continues, and it keeps going as you keep acquiring data. So you might ask, right, what's the point? You're doing phase retrieval and you're doing neural network training, right? The difference, what this enables us to do is kind of break this the need for phase retrieval in real time to keep up with the experimental data stream. What the user sees comes as the inference from the TYCO-NN network running on this edge computing device. The whole reason to keep the high-performance computer in the loop is to keep updating this TYCO-NN model to represent the fact that experimental conditions are changing. You have a dynamic sample, you have a dynamic instrument. And what this does is essentially push a model to the edge computing device, every 30 minutes or so. 30 minutes is too long to wait for phase retrieval to get real images, but because it's a neural network that's essentially doing millisecond timescale data inversion from the live data stream, you're getting results instantaneously. You just happen to be working with a model that's 30 minutes old. And if nothing changes in your sample, if you have a static sample, this doesn't matter. You could go days without doing any of this. But you have a dynamic sample, this in-the-loop online training helps you push a more accurate model to the beamline in a very regular fashion. And so using this, we were able to do essentially live inference at 2 kilohertz on a 128 by 128 detector images. And we basically just maxed out the network bandwidth that we had locally at 1 gigabyte per second. So this is what our setup looks like at the beamline. This is looking upstream at one of our tachography capable instruments. This is the sample chamber. So the X-rays come this way. This is the X-ray detector that sits there. This is the little NVIDIA Jetson device. They're really cool. They come with a shared CPU-GPU memory. So we can stream directly off the detector onto the device to do the inference. And we have another stream that gets split off that goes to the high-performance computing center for phase retrieval and deep learning. Okay, so this is what this looks like. So this is a recording of the beamline computer at the Sector 26 nanoprobe, for those of you who come to the APS. This is the raw data that we measured. This is the live inference from the neural network. This is the stitched image. So as the scan progresses, it's going to take the instantaneous predictions from the neural network and just overlay them one on top of the other. And you can see essentially as the scan progresses, you could do essentially near instantaneous tachography imaging with this approach. All right, I'm going to move on. Okay, that's another advantage to this kind of approach, where we're essentially using the inductive bias provided by the fact that we know that this experiment, this beamline, this wavelength, this sample, this is refractive index, and so on, which is that we can significantly relax the constraints required for image reconstruction. Remember, for tachography, rule of thumb, you need at least like 50% of spatial overlap with the probe. As you can see here, there is practically no overlap between adjacent probe points, right? There's a huge gap between them. Because we do not explicitly use the overlap in any way, we can just take the single shot predictions provided by TYCO-NN, stitch them together, and essentially get an image that is not too terrible. So this image in the middle was obtained with a step size of 1,000 nanometers. This is a step size of 200 nanometers. And as you can see, it's not too bad. It is not perfect. for sure. You can see there are artifacts here, for example, that are not there in the real image. But if you're looking at a dose-sensitive sample or just a sample that is too large to measure and you want to do a very quick overview, this is a way to do it. And so, with AI, you can essentially get quick overviews of samples with, 25 times, in this particular case, 25 times less beam damage and 25 times faster data acquisition. So quickly to recap this section and kind of reinforce this philosophy that we have of how high-performance computing and AI at edge is going to enhance our experimental coherent imaging and other beamlines at the APS. If you did not have high-performance computing resources, the reconstruction time is on the order of days or weeks. If you have a supercomputer plugged into the beamline, so you can move the data directly there, do phase retrieval, bring it back, we can cut this down significantly to the order of minutes or hours. Through this sort of hybrid approach where we use HPC and AI at the edge, our reconstruction time is now basically the time taken for one single inference pass through a neural network, which is in the order of milliseconds. And we can also significantly relax the data that we need to do the analysis. So I want to emphasize that this is not something that is restricted to tychography. This philosophy that high-performance computing and AI is going to play an integral part of APSU beamlines extends to all modalities at the APS. This is an example from high-energy diffraction microscopy. So HEDM is this wonderful technique that lets you reconstruct in 3D microstructural patterns with strain information. And today, this technique generates data that's sort of manageable. It takes about 1,000 CPU hours to analyze per 20 minutes or so. After the upgrade, we're looking at 10,000 CPU hours per scan. So in 30 seconds, you can take enough data to keep 10,000 CPUs busy for an hour. And so in a similar approach, and there's many aspects to this workflow and this pipeline in being able to go from the diffraction data that you measured to microstructural information. But one of the things that needs to be done is very accurate peak fitting. And so this is work from Zhengqin Liu, Hemant Sharma, and many others, including John Ulmer and Ian Foster and others. And it's a CNN that essentially takes that is able to extract the Bragg peak locations and then be very accurately be able to a sub-pixel accuracy, fit the position. And this process is 200 times faster and more accurate than pseudo-void fitting, which I'm told is the conventional way of doing this approach. And just like in the tychography case, this analysis, this is a video, let me see. Used to be a video. This is a network called BraggNN that runs on an edge computing device, takes the live stream from the detector, identifies these peaks, and then fits them at very high sub-pixel accuracy. Again, same philosophy. You train these networks on high-performance computing and run them at the edge. And sometimes you do this dynamically, especially if you have if you're physically deforming a sample, for example. Okay, so I'm going to change gears a little bit and switch to BCDI, and I'll be fast about this because I think Ross talked about this very well already. One of the things that we're really keen on is the philosophy that we need to incorporate more physics into our deep learning models and also turn them into production. Our mandate is not just in developing methods. Our mandate is to develop methods that are used by the scientific users who come to the APS every year. So this is AUTOPHASENN. And like the tychography case, this is a network that essentially does a single shot reconstruction given a 3D volume as opposed to 2D images. So it takes a 3D volume and outputs sample amplitude and phase. The cool thing about this is that this network is trained completely unsupervised. And what that means is at no point ever in training or testing did we ever show it images of what the sample looks like, right? And it's done essentially because we could use a differentiable forward model that maps the prediction from the network to the reciprocal space. So for those of you who do machine learning, this is conceptually similar to a generative adversarial network, right? So you have a generative network, but instead of taking a noise vector, it takes in a 3D diffraction image. It generates an image of a sample amplitude and phase. And instead of a learned discriminator, we have a discriminator that's hard-coded. It's a differentiable physics model that essentially maps this generated image back into reciprocal space, and so we make the comparison here. And so this entire process is completely, unsupervised, which means you never need to get these sample images. You never need to, either forward simulate them or do phase retrieval first to get to them. So here are some results from this on some simulated data. One of the things that we do is we use the neural network prediction as a prior for phase retrieval, rather than, but instead of running hundreds of iterations of phase retrieval, we can run a very small number, like 50 iterations of something like error reduction to get good results. So here's some comparisons. So this is simulated data. So we have the ground truth. This is the phase retrieval. This is the raw neural network prediction. And this is this refined process where we combine a neural network prediction with 50 iterations of error reduction. And you can see, except in this like one case, in all other cases, this combined approach of doing neural network plus phase retrieval gives you reconstructions that are more accurate than if you were to just start with phase retrieval and run things like HIO and ER. So faster and more accurate. Same thing on experimental data. So here, of course, we don't have a ground truth. So I'm comparing phase retrieval, neural network prediction, just a raw neural network prediction, and this refined process. So neural network prediction plus 50 iterations of ER. And in every case, if you look at the chi-square error, it is lower than if you were to just do phase retrieval. So again, faster and more accurate ways of doing this. And so here's a plot, again, kind of re-emphasizing this. This is the plot showing the error metric while just doing phase retrieval in dashed lines. And the reason it goes up and down is because you're switching between this HIO, which is a climbing algorithm, and ER, which is basically gradient descent. And the solid lines are the predictions, are what you do is what happens if you take the neural network prediction and then run phase retrieval. So of course we start with a much lower error because we have a good prediction as opposed to starting from a random guess. But the phase retrieval never really catches up to this NN plus ER approach, simply because we're starting with a very, very good prior. And again, I want to point out, we're not the only people working on this. Long Wu and Ian Robinson have been doing a lot of work in the same space as well. And this is a result from one of their papers where they show that the use of a machine learning initialization can significantly reduce the error as a function of iterations. The thing that really makes me happy about this is that this is now in production, and hopefully the first of many. So this is, again, a video. I hope I can play this. How do I play this? Let me tell you this. It plays it quick. It is. Okay. So this is part of the COHERE package that Ross talked about a couple of days ago. It now comes with this trained neural network as a part of the package. So you load up the package, you can then use the get the point. Okay. We can then use the prediction from the neural network as an initialization to the phase retrieval and get really good results. And all of this is done with the UI, so the user does not have to work with Jupyter notebooks or learn Python if they don't know Python, and so on. So I'll let this video play for a little bit because I seem to have lost the ability to skip ahead. So this is some of the alien removal algorithms that Ross talked about in his talk. So these are signals from external RAG peaks. And so here, rather than start from an initial guess, you will essentially at some point, Yudong will change this to an AI guess, and you can run essentially phase retrieval from that. I wish I could skip ahead. My interruptions. Yes. Okay. So here's how you choose the AI algorithm. You load a trained model, which we distribute with the package software to users. It's available for download from a public link. You run essentially a short number of ER iterations, and then I'm going to skip ahead, but essentially the end result is that you get a reconstruction that looks visually better than if you were to just run phase retrieval, and it's faster. Okay. All right, so I talked about two solutions to two different imaging modalities. I talked about PTYCHOGRAPhy for photography and AUTOPHASENN. And I kind of want to emphasize a point here, which is that we kind of have to build, in some cases, we have to build tailored solutions for different current imaging modalities. So with PTYCHOGRAPhy, we saw it was supervised training approach where we were training online, right? And this is kind of driven by this engineering constraint, which is that we need really fast inference time. We need inference time on the order of a millisecond or less on modest computing resources because our detectors are running at kilohertz, right? And so we had to use a small model. And so this model is not generalizable. It works for this experiment, this beamline, this set of conditions. With the AUTOPHASENN approach, because it takes some time to acquire a BCDI data set, it takes like 10 minutes to acquire a full 3D rocking curve data set. We don't need that sort of inference time. We can afford to do inference time that's on the order of a second or less on modest computing resources. And so we can build a network that's much bigger. If we do this unsupervised, we do this offline, which means we do this ahead of the experiment or ahead of all experiments. And so this is a more generalizable model. In our case, this generalizes to all convex objects as long as they have a weak phase. We're still working on adding defects, for example, into the sample. Okay, so with that, I'm done with this portion of the talk. I'm going to briefly talk about some of our exciting work that in the steering of experiments. So kind of this addresses this question, right? If you give an unknown sample, you put a new sample into the beamline, how should you go about acquiring data so as to maximize information gain in a minimal amount of time? And our approach goes something like this. So we first sample a few points randomly, and then we use a pre-trained network to essentially predict the most important points that you should acquire so as to maximize information gain. And this decision is made in the order of about a second or so, so our overhead is pretty low, especially given what I'll show in a couple of minutes. And what we can do with this is essentially reconstruct images with far fewer points than we would require otherwise. So the particular use case that I'm going to show is this Bragg diffraction imaging at the 008 peak, of a tungsten diselenide thin film, and looks this beautiful structure that looks like a butterfly wing is because of bubbles that form on the tungsten diselenide surface, and that's what you're seeing here with different sizes and different shapes. And the quantum people care about this because the local electronic structure is different, and so that changes things and stuff. So this network is actually something that we borrowed from electron microscopists. And this was actually developed by Charlie Bowman at Purdue in collaboration with Charudatta Phatak at Argonne, along with other collaborators at Argonne and Northwestern. And so this network is trained on one image, exactly one image, this cameraman image, which seems very popular with image processing folks, and essentially was trained on different masks of this. So essentially mask different portions of the image, train the network, and then essentially ask it to predict at which point should you sample more information so as to maximize information content. And so, the method essentially comes from this paper, and it's called SLADSnet. And we applied this to an X-ray microscope. It's a scanning X-ray microscope. So the whole workflow looks something like this. You take a few initial random measurements, build an estimation of what the image looks like, run this through this trained network to essentially predict which points to sample next, so as to maximize the reduction in distortion in the image. Rather than do this one point at a time, we modified the approach so that it samples 50 points at a time. Essentially then solve the traveling salesman problem using one of Google's OR tools, take the measurements there, get a new estimation, repeat the process. Right? Okay. So this is what the results look like. So this is the ground truth image. So this took something like a day or two to measure at high resolution. This is the AI guided approach. And you can see it mostly reconstructs all of the features using a fraction of the points required to build a high resolution image. The points in yellow are the points that were sampled by this trained network. And you can see it focuses on essentially points where there is a lot of things happening, like where there are strong gradients, essentially. So it identifies these features and then tries to fill in as much of the information around that as possible. So again, here's okay, how do I play this? Okay, so here's a video of this running again at an instrument. So we turned a multi-million-dollar piece of equipment over to this network and asked it to drive the optic. And so here's again a recording again at the sector 26 beamline for those of you who use the APS. So this red dot that you see tracing this white line is the optimized set of 50 points the network predicts at every cycle in the iteration. This is the raw diffraction data that we measure, and from which you get the intensity measurements. This is the set of points that are being measured so far and being selectively chosen by the network to sample from next. And at this point, more or less done. Okay, so I think I'm at the nearly end, at the end of my talk. I have a few outlook and questions for the audience. All of our code, everything that you saw today is freely available, all of the code and enough data to reproduce the results. We're working on making all of the data available. Some of it is just technical difficulties. We have terabytes of data, and making that available to the community is non-trivial even today. But all of the code that I showed and all of the code will always be freely available. It is part of our mandate to make these tools available to scientific users across the community, across the world. Okay, so we talked about two different ways that we're using AI at the APS: faster analysis, experimental steering, and something more long-term, which we're not going to talk about today, is learning physics directly from scattering experiments. Putting this in production is a very important part of what we do. This is happening now, as you saw with a few examples for accelerated analysis. In the next 1 to 2 years, we hope to make some of these AI for steering demonstration cases more production-friendly at the beamline. And then 5 to 10 years, I'm hoping for big things from this long-term goal that we have. So a few challenges and open questions that I have for the esteemed members in the audience today. So specific to the APSU, some of the challenges that we face are very disparate, right? So I showed 2 examples, ptychography and BCDI. Today, for BCDI, to do phase retrieval, you need about 256 to 512 cubed arrays, and this gives you a resolution of about 5 nanometers or so. So this is not bad. This is a few gigabytes of memory for phasing. So everything fits on a GPU. So it's wonderful. You get really fast phase retrieval. If you want, if you want 10x resolution, right, and that's the design case for atomic, you need essentially to phase 10x larger volume of reciprocal space. So now you need on the order of a terabyte to do phase retrieval. Right? There's no GPU that has a terabyte of phase retrieval, but of course the goal is to get a few angstrom resolution. So there is a challenge whether we're doing conventional phase retrieval or using neural networks. How do you process data sets that require so much memory? Right? This is not disk. This is memory that you need to hold, and so you need to be able to do distributed FFTs very efficiently if you want to reconstruct at this high resolution. And with ptychography, it's a different kind of problem, right? You have massive data rates, gigabyte per second data rates, requiring petaflops of peak computing power to keep up because the data stream is continuous. It's never ending. And again, today we have 5 ptychography beamlines. You're going to have 10-ish ptychography beamlines after the upgrade. And so essentially solving two techniques, essentially solving the same inverse problem, but very different in how we need to think about building a compute solution to make it work. Okay, and more open questions for for people in the audience, some of the things that we need help with is incorporating uncertainty quantification without slowing inference. So of course, there are many ways of doing this. We tend to use Monte Carlo dropout, but deep learning ensembles, Bayesian neural networks, of many different ways of doing this. All of these, though, slow inference down. So how is there ways of keeping inference fast while also providing some estimate of uncertainty quantification? Can we build foundational models for various phase retrieval applications, right? Basically, we're all solving the same inverse problem. And so with all of is it possible to build essentially universal models that are good at all types of phase retrieval, maybe just across X-ray modalities, or maybe even across different types of imaging modalities? And then there's a question of how do we abstract useful information or intelligently acquire only relevant information from massive data sets, right? So if you're doing millimeter square at 10 nanometer resolution, that's like 10 power 10, something like that, pixels, right? And there's like 100 billion stars in our galaxy, so 10 power 11. So how do we make sense of such enormous amounts of volumes? Make sense, right? That's the key point. Just acquiring this entire volume is not always very useful. And how do we effectively collect information from complementary instruments so as to span spatiotemporal scales in many modalities? If you ask a material scientist what is their perfect instrument, now they'll tell you it is something that can measure from the atomic scale to the millimeter scale, from the picosecond time scale to the second time scale, right? Can't do that today, but in combination, we have so many different instruments, not just at the APS, but at the nanoscale centers and at university facilities and so on. How do we effectively collate information from all of this to really understand science? We would love to work with you. We have data. And I'll also make a pitch. We're hiring for a postdoctoral position in physics-aware deep learning. If you have a PhD in optical, electron, or X-ray characterization, please apply. Fortunately, we don't pay like tech companies, but you'll work on building physics-aware deep learning models. You'll train at scale on some of the world's biggest supercomputers. In fact, the world's biggest supercomputer, Aurora, and you'll deploy those trained models on multi-million-dollar microscopes at the APS. With that, thank you again. It's been a pleasure. I would have really loved to come visit and spend time talking to all of you legends in the field. But I hope to do that sometime in the future. Thank you.